Topic 7F, time-domain finite difference method. You will find this method in the implementation strikingly different than what we've been talking about. We're really not going to use any linear algebra now to solve this. It'll look much more like when we talked about a numerical differentiation across the grid. So with finite difference method, how we've been talking, we write a finite difference equation for every point on a grid. We assemble that into a large matrix and solve that by backward division, and we have our answer. With a time domain finite difference method, while we could still do something like that, it's beneficial not to. We will assemble a very similar set of finite difference equations. So numerically, the behavior is the same. However, we will set up a big for loop and essentially enforce each one of them one at a time, and then go back and keep doing that. So the implementation looks very different, but the numerical behavior is very similar because they're based off almost the same exact equations. Okay, let's dive into this. I want to introduce some preliminary concepts about a time domain solution. And then by example, I'll show you what a time domain solution of the heat equation looks like. And then we'll also talk about a time domain solution to Maxwell's equations for electromagnetics. Following a bit like what we've been doing, the algorithm for finite difference time domain, or a time domain finite difference method, is really broken into two parts. The first is the formulation. So we start with the basic governing equation and we derive, and we take that as far as we possibly can until we have the final set of equations that we will implement in MATLAB or whatever programming language you're using. Then we'll talk about the implementation. So for the formulation, we identify the governing equation. Like before, we will approximate that with finite differences. After that, the formulation changes compared to what we're used to. Now what will happen, our finite difference equations will also contain a time derivative. So we will have a function value at a previous time step and a function value at the next time step. And we will solve that equation for the function value at the next time step, or the future time value. And we will call that an update equation. So we can calculate the function value at the next time step based on all the information at the previous time step. When we derive that equation, what we'll see is we sometimes have a bunch of constants and coefficients that collect that don't change over time, and it doesn't make sense to keep calculating them every iteration. And so once we derive them, that becomes something we can calculate before the iteration. So we'll lump these update coefficients into their own equations. We'll write our final update equation, and those are what we implement inside of this main loop that iterates over time. That's the formulation. The algorithm follows similarly to what we're used to. There's a dashboard where we have all the hard-coded numbers but no work. We'll calculate our grid. We'll build the device on the grid. At that point, we have the equations for the update coefficients. We have all the information we need. We will calculate the update coefficients. And every point on the grid has its own set of update coefficients. The unknown functions will initialize to their starting values. Usually this is just all 0, but could be different. When we talk about thermal analysis, maybe you set the temperature across some object to some starting configuration. Then we enter the main loop, and we have a loop over time. That's our big loop. Then inside of that, we also have a loop over space. And inside that second loop is where we enforce our finite difference equation across the entire grid. And of course, that little loop is in this big time loop, so we keep repeating the little loop. And this repeats over and over and over, and we can watch stuff move around on the grid and create little animations, and it's very neat. And in the end, we have the answer that we can post-process, we can visualize, and do neat things with. So that's how we'll do analysis in the time domain, the formulation and the implementation. Some notes about time domain algorithms in general. We can certainly implement a time domain code using linear algebra, but there's benefits if we don't. And this ties into the scalability. And if we solve a problem using linear algebra, things tend to scale not linearly. They scale exponentially. So if we double the number of points in our grid, the number of calculations could go up by 8 or 16 times. Whereas with a time domain code, if we double the number of points on our grid, it really just doubles the number of calculations. So I already touched on this, scales near linearly. The reason I say nearly is that, okay, if we double the number of points, we double the number of calculations, but it then also takes twice the amount of time for some signal or wave or phenomenon to propagate its way across the grid. So we have twice as many calculations for twice as long. So it's not quite scaling linearly, but very, very close. So the time domain finite difference method, this seems to be Thor's hammer for numerical modeling. When a problem just becomes too big, too bad, too ugly for anything else, people throw a time domain finite difference method at it. It's very easy to parallelize and to solve big, ugly, large problems. So it's very excellent for that. I can't think of a technique that's better. Of course, if you want to know the transient response of a device, and I'll talk more about that in the next slide to better understand what that is, but usually when a device is first excited, there's some fields bouncing around and doing some crazy things until finally they settle into this answer that would be what things look like after a very long time has passed. So after a long time, that's the steady state response. In a sense, the analysis we've been doing have been a steady state response. But if we want to know what happens up front, the transient response, the time domain methods are absolutely excellent for doing this. If we have nonlinear properties or materials such as diodes or just nonlinear materials, that can be done in the frequency domain, but it's very easy and inherently simple in the time domain. So for nonlinear properties, seek a time domain method. I love time domain methods for understanding and learning physical phenomena. Once your simulation is working, you can literally watch your waves or your heat fronts or other things move around and interact with the materials. So it's a great learning tool as well. So I mentioned that. Great learning tool, great for visualization. Okay, so I think I've sold the time domain method. Here I'm showing two different simulations. On the top is what we would call the steady state response, and on the bottom is the transient response. So if we were to solve an electromagnetic problem, here it's scattering from a slab, with a frequency domain model, we would jump immediately to the answer on the top. Whereas on the bottom, we understand we actually have to excite this with a source. That source hits the first interface, some bounces off, it hits the second interface, some bounces off, and this energy sort of swashing back and forth. But over time, that transient response settles into the steady state response. So in a frequency domain simulation, we jump immediately to that steady state response and we miss everything that happens in the beginning. And that's sort of a shame. In the transient response, we see that. And so these time domain methods can do that and show us the transient response. And very often there's a lot that we can learn from that. And in this simulation on the bottom, maybe you notice that the behavior went from blue to red. And I'm just trying to show the transition between the transient and the steady state response. Once the line is red on the bottom, it was the steady state response. So you can rewind the video and watch that over again. So nothing's better than an example to teach this method. So let's look at the time domain solution of the heat equation, see what that might look like. So first we have to set up our problem. Let's say we have this bar of some strange material, and at first it is held all at 0 degrees C. But suddenly at time 0, that right-hand side of the bar is held at 350 degrees C. So clearly that end of the bar will be heating up, and we should be able to watch the temperature profile on this bar change with time, and we would like to see that. To make this a little bit more strange, the thermal diffusivity, which sort of characterizes how quickly heat can move up and down this bar, is described by this parameter alpha, and that is not a constant here. It's a function of the length over the wire or the bar. So that's our problem. Let's see how we would solve this using the finite difference method. Well, we have to identify our starting equation, and in this case, it's the time domain form of the heat equation. Now, in this equation, the capital T is temperature, and that is a function of x, although I'm not showing that explicitly in the equation. The little t, the lowercase t, that's time. And alpha is the thermal diffusivity talked about on the previous slide. And just to give you a feel of the numbers, I've listed that for several items. So wood, for example, does not conduct heat very well at all, so that has a very, very small thermal diffusivity, whereas metal is more 10 to the minus 4. The del operator, the little upside down triangle, that's sort of a three-dimensional derivative, and so del squared, that's called the Laplacian. It's a second order three-dimensional derivative of the temperature. Now we're analyzing a bar, so one of the first things we want to do is reduce this to a one-dimensional problem instead of a three-dimensional problem. But the equation on this slide is for full 3 dimensions, and this is our starting point, so we call it the governing equation. So we'd like to reduce this to 1 dimension because we have this skinny little bar. Now, if that bar were very fat, this may not be an accurate thing to do. So for a skinny bar, this is a pretty accurate way to analyze the problem and simplifies our math. So the first thing we do is we expand this into, so we can see the full 3-dimensionality of this. So we expanded our Laplacian. And we will assume that this is a 1-dimensional problem across x, and that's a good approximation if the dimensions of that bar in y and z are very small. So if the temperature in the y and z direction is rather instantaneous, we can just cross off those derivatives. And we've reduced our problem to 1 dimension. So here is our revised governing equation, now reduced to 1 dimension. And here I explicitly put in what these different variables are a function of. So temperature T is a function of position and time. That thermal diffusivity is only a function of position. So let's move on with this and see how we can solve it. So there's our governing equation from the previous slide. We'll make a first guess at how we could solve this using finite differences. So I took a stab at the finite difference for the first term, the derivative of temperature with respect to time, and then also the second term, which is a second order derivative with respect to space. And these are finite differences that we have been discussing for a while. Now remember our fundamental rule with a finite difference equation. Every term in the equation has to exist at the same point in time and space. So we need to look at these terms and see what's happening. So our first term, if we look at our coefficients, we have a t plus delta t and a t. And so if we interpret that as a central finite difference, we see that that term exists at t plus delta t over 2. Now our alpha term is not a function of t, so we really can let it exist wherever we want to. I'll call it t. Then our last finite difference equation, that's a second order finite difference equation. If we interpret that as a central finite difference, it exists at t. So right away we see we have a bit of a problem. That first term does not exist at the same time as the other terms in the equation. And so that's a problem we need to talk about. There's 3 main ways that we can do this, and the first 2 are kind of simple and maybe cheating in a way. Let's just look at that first finite difference and interpret it as a backward finite difference instead of a central finite difference. So we can just declare that term to exist at time t, and that fixes our problem. And we can do this. And in fact, we will do this when we actually do our solution because it's very easy and it can work a lot of times, but it is not necessarily unconditionally stable. There are times where this could blow up on us. So it's not necessarily the best, but it is very simple. Similarly, we can interpret that first term as a forward finite difference. We can write the t and the t plus delta t minus delta t parts a little bit differently to make this work. But again, we just simply define that as existing at time t, and that fixes our problem. Very simple answer, but not necessarily unconditionally stable. There's a third way, and this is probably the better way. We can look at that second term, the alpha times the second order derivative, and we can interpolate that to exist at the midpoint. If we do that, every term in this equation exists at t plus delta t over 2. So this is a healthy way to do this, probably the best way to do it, but you can see from the equation that it is a bit more complicated. Solving this way is called the Crank-Nicholson scheme. However, we're going to proceed with one of the ones on the previous slide instead of this one, just due to the simplicity in the math. So let's go with solution 1. And so all terms now exist at time t simply because we just declared it to be that for the first term. So instead of writing this explicitly as functions of x and t, let's now write this in terms of array indices. So the array index I is position, and array index k is the timestamp. So k just refers to the current time step. K plus 1 refers to the temperature at the next time step. So we only have one term like that here, so you can imagine solving this for t at k plus 1 in terms of the t's at the previous time step, and that's our update equation. But it looks a little bit better written in terms of the array indices instead of explicitly x and t. So we solve that for t at the future time step, and we arrive at our update equation. And we will implement that equation for every point on our grid as a function of x. So if we have 100 points on our grid, we write this equation 100 different times, very much like we did when we did numerical differentiation. We'll put that in a big loop, and we will update all the values of t. Before we solve that, notice we had this collection of terms. And these terms are not changing over time. So why do that calculation at every point, at every iteration? That doesn't make sense. So we will call that an update coefficient. We will calculate it ahead of time. Now, since that alpha term is a function of position, the update equation is a function of position. And in fact, we store that as an array, which I'm implying with that subscript I. So before we even get into our main loop over time, we will calculate the update coefficients and then implement this update equation at every point on the grid. We have a stability condition. There's a lot we could say here, but if we look at the numerics, just numerically, every time step, it is impossible for a disturbance to go more than one cell in a single time step. So we have to make sure that this heat front would not physically need to travel faster than that, because it can't do that numerically. So we set our time step so that the actual heat wave would be slower than one cell per time step. So that's the simple answer to this, and we get a stability condition. And that's how we calculate our time step. And as long as it's smaller than that certain value, we will have a stable code. Given all that, we can revise our algorithm. So we'll have our dashboard, initialize MATLAB, all that sort of stuff up front. The first work we'll do outside of the dashboard is to calculate our grid. How many points and what is the cell size? Step 4, we build the device on the grid. In this case, it's just calculating that alpha, the thermal diffusivity, as a function of position across our grid. So we'll have an array alpha. Then we need to calculate a stable time step. So what is dt? We'll use dt to be our time step, and we might want to calculate an nt, the total number of time steps. We could do it that way, or we could just run our code and checking the changes in temperature as a function of position, and when we don't see changes anymore, we can stop the function. So either way works as a good stop condition. Here I'm just saying we'll calculate total number of iterations. So before we enter our main loop, we want to calculate our update coefficients because these don't change over time, and this will be stored in an array. At that point, we'll initialize our array. So we're setting the temperature to 0. Notice we have a T and a T2. I'm using T2 as the temperature at the future time step because we'll have to store both. And that's because we don't want, if we're in the middle of updating our temperatures, then on one side we would be using new values of temperature, on the other side we will be using old values, and it's not proper to do that. So we'll calculate the new temperatures in T2 only from the old temperatures stored in T. So we have to initialize both of them to 0 to start with. At this point, we enter our main loop. So this iterates over time. Inside the main loop, there's another loop. So this is step 8a, and this is when we loop over x, and we implement that update equation at every point in our grid. Once we've done that, our numbers may have changed at the first and last cell, but in the statement of our problem, we're holding the left side of our bar at 0 and the right side of the bar at 350. So we have to go in and overwrite the values on the first point and the end point to enforce those boundary conditions. At that point, the update's done. We might want to do some other things. Maybe we want to record intermediate results. Maybe we want to visualize the results. We want to watch the temperature as a function of time. Well, after the time loop is over, the simulation really is over, and we recorded some things probably. Now we can post-process them to learn something. Maybe we visualize the results. Maybe we've been rendering a movie, and we have this movie of temperature as a function of time. But that's it. And really all time domain finite difference methods follow a very similar flow. They'll just have different numbers they're calculating, different update coefficients, but they all really have the same flow to them. Okay, now let's talk about time domain solution of Maxwell's equations. So the time domain solution of Maxwell's equations is called finite difference time domain. Now from that title, that really says nothing that is actually electromagnetics, but if you're reading and you read the words finite difference time domain, almost always they're talking about an electromagnetic solution. In this case, the information primarily comes from two of Maxwell's equations that are called the curl equations, and I've written them here. And the two equations are working in concert with each other. Now, physically, everything's happening at the same time, but to implement this in time domain, we're going to pretend that one equation happens before the other. And so perhaps we start on the left, and we will calculate the curl of the electric field. Based on that curl, we will update our value of h, because we can see a time domain derivative there, and you can imagine solving for h for the future time step there. And then the mu, the permeability, is just a proportionality constant. It tells us how much h changes in response to a curl in the electric field. So in this first step, we're updating h based on the curl of E. Now, very similar in the second step, we will then calculate the curl of the H field and update the electric field based on the curl of H. So we update H based on the curl of E, then update E based on the curl of H, and then we go back and update H on the curl of E, and it's a back-forth algorithm, sometimes called a leapfrog algorithm. So it's EH, 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 and it's constantly bouncing back and forth, back and forth, back and forth. And this iterates over time. Now, each one of those equations also has a little tiny loop going over space. And that's the heartbeat of finite difference time domain. Now, for three-dimensional problems, we talked a bit in other lectures about how we stagger our unknown variables. Well, we have two unknowns here, an electric field and a magnetic field. They're vectors and have X, Y, and Z components. And in fact, we stagger them in the manner I'm showing on this slide. That's called the Yee cell or the Yee algorithm. And we use that to discretize and write our finite differences. So I'm not going to talk about these spatial finite differences. You've seen that in previous lectures. But I can talk a little bit about the time derivative. We now have two equations. And since we've staggered them in space, it makes a little bit of sense that we would also stagger these in time. And we will define the electric fields to be at time step 0, delta t, 2 delta t. I'll call that the integer time steps. The magnetic field H will be defined to exist at delta t over 2, 3 delta t over 2, 5 delta t over 2. I'll call those the half time steps. So E and H are not only staggered in space, but staggered in time. And that lets us write really nice finite difference equations. So in this step, all we've done was do a finite difference approximation for our time derivatives. And we talked about staggering E and H in time as well, as you can see from those equations. Given our equations, we did our finite difference for time. Also in this step, we would have done our finite differences for the curl. I'm not going to write that. So we take these two equations and we solve for the field values at the future time steps, and we arrive at the update equation for electromagnetics. We'll see the delta t over mu and the delta t over epsilon. Those are our update coefficients. That is also something that we can calculate ahead of time to help speed our simulation. So those are our update coefficients. We have a similar stability condition that we had for heat for electromagnetics, but it's the same thing. It's physically impossible for a disturbance to travel farther than one cell in one time step, just due to how we've structured our finite differences. Therefore, we have to make sure that the physical wave would not need to propagate faster than that. So we choose a small enough delta t that the physical wave would not travel more than one cell in one time step, or it can go unstable. So the basic Courant stability condition is this middle term. Now I've modified it a little bit to something easier and also a little bit more useful. I incorporated a minimum refractive index across the grid, because sometimes if we don't have air everywhere, maybe we have a refractive index material that's higher than 1 over the entire grid. Sometimes we can get away with a larger time step, and that's neat to account for. Other times, if we're simulating metamaterials or doing some kind of effective medium thing where the effective refractiveness can be less than 1, the original Courant stability condition will not work, and we really do need to account for the minimum. Also, rather than have the delta x, delta y, delta z, those are our grid resolution parameters, I just find the smallest one of those and call that delta min and use that in the equation. So it's an easier equation to use and also accounts for the minimum refractive index. So in practice, in my codes, I use this for the Courant stability condition. And I just make sure that my time step is smaller than that. So when I have students implement the finite difference time domain algorithm, we had those two basic update equations. I call that the heartbeat of finite difference time domain. I have them implement that. And so we're updating E from H, H from E, EH, back and forth, back and forth, back and forth. And if we look at the simulation on this slide, we're simulating, but nothing's happening. And that's exactly what should happen right now. Nothing should happen. If something were happening, there'd be some kind of problem, because everything starts at 0. So if we update, if E is all zeros and we figure out our new H, H should still be all zeros. So it's a good check to make sure that your initial heartbeat is correct. If we get all zeros, that doesn't necessarily guarantee correctness, but if we saw something happening here, that would definitely mean that something is wrong. So we are running EH, 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 back and forth, back and forth, back and forth, but nothing's happening. That's exactly what should happen. Now suddenly we start throwing numbers into the grid somehow, and we're updating backward EH, 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 EH. Now we can start seeing those numbers travel across the grid. That's the next step. So we add what's called a simple soft source. We'll talk more about what a soft source and a hard source is later, but this is just the simplest way to get energy or power into our simulation. So we did something in the middle, we just overwrote with a value, and suddenly we see stuff travel left and right. The blue line's the electric field, the red line is the magnetic field, and we just use simple Dirichlet boundary conditions so they reflect off of the edges, and everything seems to be working. Those aren't exploding. We got energy into our simulation, and that's about really all we should see at this point. So let's go on to the next step. We don't want those pulses to reflect off of the boundary, so we added an absorbing boundary condition. In this case, it's a perfect boundary condition, and it just makes it look like these waves go off to infinity. Now, if we zoomed in on the y-axis, we would see that something reflects off that. There's really no such thing as an absolutely perfect boundary condition, but what reflects may be 6 orders of magnitude down, and that's usually perfectly fine for a simulation. So really, this soft source that we're using isn't really what we want. It's just something really simple to do to throw power against our boundaries to make sure that our boundaries work. So our boundaries work now. Now we can get a little more sophisticated with the source. And we do what's called a total field, scattered field source. An easier way to think about this is just a one-way source. We only want to throw power in one direction. Because normally when we inject power, it's all the way to the left-hand side of our simulation. That's where we inject our power. We throw it to the right. It bounces and resonates with inside some kind of device, and we record what gets reflected and transmitted. So since we move our source all the way over to the left, we don't want to propagate anything backwards because of 2 reasons. One, we have less control over where the power is going in our grid. But secondly, that backward energy, some will reflect off that interface because we can't really have a perfect boundary condition. So something will reflect off of that boundary, and we don't want that, and we don't have to have it. So by using this total field scatter field technique, we're able to incorporate a one-way source. Think of it like a flashlight. You turn on a flashlight, the beam goes one way and not backward. So it's a great way to implement a source in the finite difference method. Now we want to move that source all the way over to the left. And so we're throwing the power to the right. Nothing goes backwards. We can see our electric and magnetic field. At this point, we're just transmitting through air. So we'll add our calculation of transmission and reflection. And since we're only simulating air, we should see 100% transmission, 0% reflection. And that really is exactly what we see here. And by the way, what looks like a little bit of noise behind that pulse really isn't noise. It's just when MATLAB draws the graphics, there's a field value right on the threshold between 2 pixels, and that's what you're seeing. But there really is not that noise in the simulation. So we're getting 100% reflection, 0% reflection, and this is something I always do with a new numerical method. I transmit transmission through nothing. And that means we should get 100% transmission and 0% reflection. It's a great check to make sure that the calculations are correct. And like before, if we do get 100% transmission, 0% reflection, that isn't 100% guarantee that things are correct. But certainly if we didn't get that answer, that would mean that things are wrong. Now we're finally ready to add a device in there. So we can add a device. We can watch our fields interact with it, and we're calculating transmission and reflection. Now watch what happens. We now suddenly see this dashed black line. The dashed black line is transmission plus reflection. That should be 100% all the way across, and it's not, and that's crazy. What on earth is going on here? Well, what's going on is we're simulating a resonant device. There's still energy stuck inside that device. There's waves bouncing back and forth. And unfortunately, in a time domain simulation, the only thing we can do is let this run and run and run until finally it leaks out either as transmission and reflection. And eventually we will see that conservation line, that black line, settle out to be a flat line. And once that's flat, we know that our simulation is finished. And if it never does become flat, we know that something is wrong with our simulation. This is something I always do with my personal simulations, is plot that conservation line. Now clearly, if you've incorporated gain or loss into your simulation, then your conservation would not be at 100%. It would come below or above if it was loss or gain. So one thing I do in my simulations is if I want to incorporate loss or gain, I'll get everything working, I'll write my code, but I'll turn that gain or loss off. So I'll run a simulation with no loss, no gain. I'll make sure that I get my 100% conservation. Then I'll turn on the loss or gain. It's just sort of an extra level of assurance that things are right within your model. So we're done. We've developed a full one-dimensional finite difference time domain algorithm. Another thing that I want to point out is notice the sequence that I developed this in. And when I'm developing codes, this is the type of sequence that I would use. I would never ever jump into programming what you're seeing here. So this is sort of the final big bad ugly simulation. And if I waited until I got all the code written to hit run that first time, I would have a really hard time figuring out where my errors are. Whereas if I write my code in steps like this, I'm much better able to catch my errors as I go. Okay, so that's one-dimensional finite difference time domain. Now, because you can't run movies in the electronic notes, I just did a sort of a freeze frame conceptual image of what each step was talking about. So nothing new here, just still images. Let's talk about the different types of sources. This is a simple hard source. So I go into the grid and I just overwrite a value somewhere with the source. Now watch what happens. When a pulse hits that, it reflects off of it. And that's because I'm just doing a brute force overwriting of information on that point. And things can't pass through it. And this is usually bad because if my waves bounce off that artificially, then they're going to re-enter my problem and probably disrupt my results. So the simple hard source is by far the simplest source, but it's also by far the worst source and probably only talked about academically. I'm not sure people actually use this source for anything real. So rather than just overwrite with our source, what if we just took whatever field value was there and added the source? This is called a soft source, and watch what happens. Reflected waves pass through it as if it was not there. So we call that a simple soft source. This is much more useful than the hard source because waves will just pass through it. Then a specific case of the soft source is the one-way source. And I use the total field scatter field technique to implement that one-way source. It's a soft source, so when power reflects off our device, we inject this one-way wave. When power reflects off something, when it goes back, it's able to pass through that region where we injected the source. If that were a hard source, that would not be the case. The one-way source also gives us the ability to better control the amplitude of the field that we're injecting. And it doesn't send any energy backward that would hit that left boundary. Some would still artificially reflect. It would come back and cause a little bit of noise in our simulation. Would that be tolerable? In most cases, probably yes, but it's simple to eliminate that here. So I'm a big fan of this total field scatter field technique for injecting one-way sources. That works really well for me. It's not the only way. Now for calculating transmission and reflection, let's say the simulation's running In the dashed red line on the left and the dashed blue line on the right, I am recording what gets reflected and what gets transmitted. Now notice I excited this slab of dielectric with an impulse, a short impulse. That means when I'm recording, I am recording the impulse response. And so then if we Fourier transform the impulse response, then I get my reflection and transmission spectrum. A little bit more to say on how we do things here, but that's the short story. We're recording the impulse response, and we're Fourier transforming it to get reflectance and transmittance. So here's a block diagram of a one-dimensional finite difference time domain algorithm. A little bit more going on here. So other than all the dashboard, initialized MATLAB kind of stuff, we come into the main algorithm. Step one, we're calculating all of our grid stuff. So we're calculating how many points we have, the cell size. Then we move down and we build our device on the grid. So our device could have a permittivity and a permeability at every point on our grid. So we go ahead and do that. Once we have that, we're ready to calculate the time step. That's the Courant stability condition that ensures that our physical wave would not need to be faster than we could actually make the wave move across our grid. At that point, we calculate the source. We're using a Gaussian source. And really, there's only two tricks here. First, we want to make sure that the Gaussian is narrow enough or quick enough that it includes all the frequencies we want. And the second thing is, we don't want to start our source right in the middle of that Gaussian. So we want to offset that Gaussian in time. So when the simulation starts, everything's zero, and we sort of ease in and ease out of that source. Otherwise, it's just calculating a simple Gaussian. Well, now we can calculate our update coefficients at every point. We have two update equations, so we have two update coefficients. And in more complicated codes, the update coefficients, they get uglier, and there becomes more of them for each update equation. So in higher dimensional codes, this can be more work. We then set all of our fields to 0. We have some boundary terms also to fit to 0. That's not something we're talking about here, but that's how we handle this perfectly absorbing boundary. Then we enter our main loop. So we have a main loop that's iterating over time. The first thing inside that main loop is another loop that iterates over our grid. And here's where we update H from the curl of E. Once we've updated that across the entire grid, we come out of that loop and update these terms at the boundaries to help us do the perfectly absorbing boundaries. Then we enter a second little loop over the entire grid where we update E from the curl of H. When that is done, we have some boundary terms to update. At this point, we've updated the fields everywhere. And so now we want to inject our source. So electromagnetically, we're done here. The only other thing we might want to do is visualize the fields or record something happening. And then our main time loop goes and goes and goes, and we're constantly going back and forth, EH, and injecting a source somewhere and absorbing waves at the boundaries, and then we watch things move around, we record, we learn, and we're finished. And that's it. That is finite difference time domain. So this is something that can happen called numerical dispersion. So let's look at this first animation on the top. So here's what we want to happen. We want to inject a source, and we want to watch that source propagate all the way across. And those pulses always stay those pulses. That's what should happen. Now, if we don't do things very well when we set up our grid, maybe we have poor resolution on our grid, or there's some other things that can do this. Let's watch what happens. We inject those same pulses, but watch what happens as it's propagating. Notice these little ringing tails developing on the back end. That's not physical. That wouldn't happen with a physical wave, not traveling through air anyway. And so this is just a numerical artifact, and this can lead to a lot of error. So that's called numerical dispersion, and all time domain algorithms will suffer from something similar to that. And we really need to take care when we set up our grid parameters and time steps to ensure that that artifact is small enough that it won't cause any problems. The simulation or the movie that's happening at the top, there is still numerical dispersion there. It's just small enough that we don't observe it over the scale of our simulation. So in a practical sense, we've eliminated it, but it's never eliminated. It's just reduced. Now to develop a two-dimensional finite difference time domain, we go through a similar set of steps. Now, I'm not showing the first step here where I would have a student just implement the update equations where nothing's happening. That's kind of boring, but that is definitely a first step. Here, what we're doing is a simple soft source on a two-dimensional grid, and we're using simple Dirichlet boundary conditions. So you'll notice at the beginning of the simulation, that pulse started at some point on the grid. When it hit the edges, it bounced off. So we're about to see this for a second time. Simple soft source somewhere in our grid, and when that wavefront hits the edge, it bounces off. So we use the Dirichlet boundary condition, so we're expecting that bouncing. That's not a problem. Really what we're looking for here is to make sure that the fields aren't exploding, and everything here is on the order between 0 and 1. If we start seeing 10 to the 4, 10 to the 6, and 10 to the 34 or whatever, we would say that our simulation is going unstable. And that can happen even if we make just a simple sign error somewhere. So this is just a great check to make sure things are right. We don't really like this source that we're doing, but it's a simple, convenient way just to throw power at these boundaries so that we can test them. Then we can also test our periodic boundary condition now. And here, now when that wavefront hits the edge, it doesn't reflect, it enters from the other side. So now we have periodic boundaries. So it turns out the last slide and this slide, steps 1 and 2, are pretty easy. We want a way to absorb the waves at the boundary, and the boundary condition we use for the one-dimensional finite difference time domain does not work for 2 dimensions. And instead, the state-of-the-art is something called a perfectly matched layer. And unfortunately, a finite difference time domain, this is just a tough boundary condition. It really makes the code tedious. It makes it not clean. It's unfortunately, because the PML is a frequency domain concept, when we bring it into the time domain, it gets a little bit ugly. Conceptually, looking at the simulation, not much new will be happening, but the code's a lot bigger and uglier once we do that. Okay, so now we built in this perfectly matched layer. To make a very long story short, we've built in loss in the outer cells of our grid. So when that ring hits those boundaries, it gets absorbed instead of being reflected. Simple conceptually, but this is a very ugly step in our code for finite difference time domain. But a great illustration of what a perfectly matched layer is, and also a great way to test our perfectly matched layer. Okay, at this point, maybe we want to simulate a periodic structure. So we'll use periodic boundary conditions on the left and the right, a PML on the top and the bottom, and now we're going to incorporate a total field scatter field source, or this one-way source. And I always like to first inject the source in the middle of the grid, just so I can easily see if there's anything that's traveling backward. It's a great way to test my source. I don't want it in the middle. I will eventually move it up to the top, but this is an intermediate step that I do, just to make sure everything is working. At this point, we can move that total field scatter field source to the top. We still have air everywhere, and now we've added the ability to calculate reflectance and transmittance. So if everything's working correctly, we should see 100% transmission and 0% reflection, because we're just simulating transmission through air. So another intermediate step. So everything's working here, so we're ready to add a real device. And that's the last step. Here we add a diffraction grating. A wave hits that, it diffracts, does some crazy stuff, and we're calculating transmission and reflection. And now that we have a device in there, we can see some crazy behavior in that conservation line, the dashed black line. And it's not at 100%. That's because there's still power or energy resonating in our device, and we have keep running this until it leaves. To my knowledge, there's not really a clever solution to this other than to let the simulation run and run and run. But it does eventually flatten out. If it didn't flatten out, then something would be wrong. So we can conclude, okay, we have now a working two-dimensional finite difference time domain. And notice we took it through a very similar set of incremental steps like we did for the one-dimensional finite difference time domain. And this is very representative of how I write my own codes. The more steps I can add, the better. I never ever just jump into the big, bad, ugly thing that I have in mind. I build it in steps of increasing complexity. And that's a very, very big deal and great advice to you writing your own codes. So because you can't run animations in the electronic notes, here's just sort of a freeze frame of each step and what it looks like. The last slide I'll show you, this is a simulation done by some brilliant students a number of years ago as their final project for the finite difference time domain class. And it's a simulation of a radar system. And you can see two little fighter aircraft that were hit with a radar beam and they reflected. And on the right is what the receiver is seeing. And in principle, we would process that signal from the radar and learn something about what we're looking at. Another thing this is very good for is the visualization. Even though this is a pretty complicated thing we're doing, visually it's very simple. A sixth grader could look at this and understand what's happening. And that's one of the beauties of finite difference time domain. It really lets you understand what's happening, understand the physics of devices, because you can watch the field bounce around. Great movies to show people too, and I love that part of this method. So that's it. That is time domain finite difference method. I hope this is helpful.